Good morning, students. Welcome to session 1 of Hilbert spaces class. In the previous chapter, you have studied nonlinear spaces and Banach spaces. These spaces enjoy both linear properties as well as metric properties. Although the norm on a linear space generalized the concept of the length of a vector, but the main geometrical concept missing in the abstract normed and Banach spaces is the angle between the vectors. In this chapter, we study linear spaces having an inner product. The inner product is a generalization of the usual dot product. The concept of inner product on a linear space leads to an inner product space, and a complete inner product space is called a Hilbert space. Okay, an inner product space is a special type of normed space which possesses additional structure and inner product. The theory of Hilbert spaces does not deal with angles in general, but the presence of additional algebraic structure of inner product greatly enriches the geometric properties of the space. Most significantly, it enables us to introduce the notion of perpendicularity of two vectors, and the geometry corresponds in several fundamental respects with Euclidean geometry. In particular, this leads us to the important projection theorems, a generalized theory of Fourier series, a most sensible definition of self-adjoint operators, and a powerful body of the theory based on this new concept. Okay, so in this chapter, we concerned with the geometrical properties of the inner product space and Hilbert spaces. Okay, so let us take up the formal definition of an Hilbert space. Say look here. So let H be a complex Banach space, means a Banach space over a complex field. Then H is called a Hilbert space if a complex number denoted by this symbol called the inner product of x and y is associated to each of the vectors x and y in such a way that inner product of xy is inner product of yx conjugate, inner product of alpha x plus beta y comma z is alpha into x comma z plus beta into y comma z, and the third one is inner product of x comma x is norm of x whole square, or norm of x is what? Length of a vector x is inner product of x comma x power of 1 over 2. This holds for every x, y, z in H, and alpha and beta are scalars. Okay, so if H is a complex Banach space, if it has a inner product, then it's called a Hilbert space, or in other words, an inner product space denoted by x with the inner product over the field K is said to be an Hilbert space if x is complete with respect to the norm given by norm of x is equal to inner product of x comma x power of 1 by 2. That means in a complete inner product space is called the Hilbert space. The Hilbert space x over the field K is said to be real or complex inner Hilbert space accordingly as the field K is real or complex. Clearly, a Hilbert space is a special type of Banach space with the addition condition that the Banach space should contain the inner product, right? On the other hand, a Banach space will be a Hilbert space if there exists an inner product, on x such that inner product of x comma x is norm of x whole square for every x belongs to x, means that norm is defined from this inner product. Okay, or norm induces a inner product. Okay, however, a Banach space in general may not be a Hilbert space. A Hilbert space is a Banach space, but a converse Banach space may not be a Hilbert space. Okay, I understand now. So Hilbert space is a complex Banach space with the inner product, or a Hilbert space is a complete inner product space with the norm defined on it. Okay, so let us take up few examples. The inner product space Rn, the inner product space, say Rn equipped with the induced norm given by norm of x is inner product of x comma x power of that's equal to summation I is equal to 1 to n xi I square power of 1 by 2, where x is having the coordinates xi1, xi2, etc. xin, where each xi is a real number that belongs to R. It's an element of Rn. Okay, so he is a Hilbert space because you know that Rn is complete under this. Okay, it is a Hilbert space. Next is the Banach space L2n. Look here, this is a particular case. The Banach space L2n, LP you know that, but it is a L2n. The Banach space L2n consisting of all n tuple of complex numbers with the norm of a vector x defined by norm of x is equal to summation I is equal to 1 to n mod xi square power of. You know norm of, in LP you know norm is defined by summation I is equal to 1 to infinity xi power of p whole power of 1 by p. Here it is L2 and it is the L2n space. Only ns we have finite sequence of elements. So and the inner product is defined here. Inner product of x comma y is summation I is equal to 1 to n xi into yi bar. You know this is an inner product space that you have studied in your linear algebra classes in the second semester, right? This holds for every y with coordinates y1, y2, etc. yn belongs to L2n. This is a Hilbert space. The Banach space L2n is a Hilbert space. Okay. Now you consider the linear space LP 1 less than or equal to p less than infinity, where p is not equal to 2. Okay. Equipped with the norm given by norm of xp is summation I is equal to 1 to n. Sorry, this is the linear space summation I is equal to 1 to infinity. Summation I is equal to 1 to infinity mod xi power of p whole power of 1 by p, where x is equal to xi belongs to LP, is not an inner product space. If it is not an inner product space means inner product cannot be defined on this. This is a Banach space. So inner product cannot be defined on this, and so it's not a Hilbert space. Why it cannot be an inner product space? Let us see here. Say for this you consider one of the elements, say x is containing the sequence -1, 1, -1, 0, 0, etc. and so on, because it is an infinite sequence of elements, and y is -1, 1, 0, 0 and so on, zeros. So you consider these two are elements in LP. Then what about norm of xp? Norm of xp is, xp means norm of x only, corresponding to this norm corresponding to LP, that we denote it by norm of xp. So this is equal to what? So the sum of summation I is equal to 1 to infinity x mod xi square power of 1 by 2. So according to that, the sum of this is 2 power of 1 by p. Similarly, norm of yp is also 2 power of 1 by 3. And x plus y is what? So -1, -1, -2, and this is 0 and so on. Therefore, norm of x plus yp is 2 and norm of x minus yp is 2. Thus, norm of x plus y p square plus norm of x minus y square is equal to 8, and 2 times of norm of xp square plus yp square is 4 into 4 power of 1 by p. So you can see that this will be not equal to this. So what is parallelogram law says? So if it is an inner product space, then parallelogram law must hold good in this space LP, but the parallelogram law is not satisfied here. Therefore, it is LP, P is not equal to 2 is not an inner product space, and so it is not a Hilbert space. Okay, parallelogram law fails to hold here. Okay, similarly, but you can see that LP is in fact LP is a Banach space. LP is complete, we have proved. In fact L infinity is also complete, that also we have shown, right? So next is this definition. Let X be a linear space. It may be real or complex linear space. A non-empty subset M of X is said to be a convex set. A non-empty subset M of X is said to be convex if X comma Y belongs to M implies 1 minus alpha times X plus alpha into Y belongs to M, where alpha is a real number such that alpha lies between 0 and 1. Okay, so this is what? This is the equation of line segment. So it says that whenever X comma Y belongs to M, then the line joining X and Y also lies in M. Then we say that the non-empty subset M as convex set. The convex set is nothing but for a very pair of elements, a line joining that pair of elements must also in that set, then such sets are known as convex sets. Okay, for example, see here, this is a convex set. If you take like this, any set of this type, say any pair of elements you take, definitely that element, that line segment joining say X and Y means that line segment joining these 2 points lies in this set itself. Says for example, if I take a set of this type, what will happen here? So I will take X here and Y here. X is this and Y is this. What will happen? A line joining this X and Y lies out of this set. This is out of the set, therefore this line lies out of the set. Such set is not convex. Okay, such set is not convex. Okay, answer now? Yes. Now look here. Now if we take alpha is equal to off, then what will we can see that M is a convex subset if and only if X plus Y by 2 belongs to M. If XY belongs to M, then X plus Y by 2 also belongs to M, taking alpha is equal to 1 over 2. Okay. Now let us take the first theorem of this Hilbert space. This theorem says a closed convex subset M of a Hilbert space H contains a unique vector of smallest norm. A closed convex subset M of a Hilbert space H contains a unique vector of smallest norm. Unique smallest norm means what? Okay, any element having the norm in that set is very small. Okay, so I'll take, let D is equal to infimum of smallest of norm of X where X belongs to M. Okay, answer now. Let D be the infimum of norm of X where X belongs to M. Then what will happen? By the definition of infimum, there exists a sequence of elements Xn in M such that norm of Xn converges to D. This is by definition of an infimum. So I'll choose let Xn comma Xm be any 2 elements of this sequence Xn. Now since M is convex, Xn plus Xm by 2 definitely belongs to M, because M is convex. Now then by definition of D, so now D is the smallest of norms of the elements of M. So by definition of D, norm of this element should be greater than or equal to D, because D is the smallest. This implies norm of Xn plus Xm is greater than or equal to 2 times of D. You call this by 1. So squaring this term, you get norm of Xn plus Xm square is greater than or equal to 4D square. So if it is like this, x is greater than y means minus x is less than minus y. Accordingly, minus of norm of xn plus xm whole square is less than or equal to minus 4d square. Okay. Now, using parallelogram law, we get norm of xn plus xm whole square plus norm of xn minus xm whole square is equal to 2 times norm of xn square plus xm square. Okay. Or this implies xn minus xm whole square is equal to, you transform this term to right hand side. This becomes minus norm of xn plus xm square plus 2 times of norm of xn square plus xm square. But this is less than or equal to minus 4d square plus 2 times, this is 2 times norm of xn square plus xm square. But as n comma m tending to infinity, norm of xn converges to d, norm of xm also tends to d. Therefore, this becomes, what will happen for this term? This becomes, as n and m tending to infinity, we get norm of xn minus xm square is less than or equal to minus 4d square plus 2 times of d square plus d square. Total, the sum is 0, means norm of xn minus xm tends to 0 as m comma n tending to infinity. Then you can declare that xn is a what? Xn is a Cauchy sequence in M. Xn is a Cauchy sequence in M. Now, M is a closed subspace of a complete space, therefore M is also complete. Now, Xn is a Cauchy sequence in M which is complete, means what will happen? There exists some element, say x0 belongs to M such that Xn converges to x0. This implies what? Norm of Xn converges to norm of x0. Now, norm of x0 is equal to norm of x0 means limit of xn, that's equal to limit of norm of xn. Limit of norm of xn is d, therefore norm of x0 is equal to d. Thus, x0 is a vector in M with the smallest norm d. Thus, x0 is a vector in M with the smallest norm d. So, thus we have proved the existence of such vector. Now, we have to prove such x0 is a unique element of M, means okay, there exists only one such element. If possible, suppose there exist two elements x0 and y0 in M such that norm of x0 is d as well as norm of y0 is also d. Now M is convex and this is convex. Now M is convex and x0 comma y0 belongs to M implies what? X0 plus y0 by 2 belongs to M. This implies what? D is, means norm of this term, norm of x0 plus y0 by 2 is greater than or equal to d. Okay. This implies norm of x0 plus y0 whole square is greater than or equal to 4d square. Again apply the parallelogram law. It gives norm of x0 minus y0 square plus x0 plus y0 square is equal to 2 times norm of x0 square plus norm of y0 square. So this implies norm of x0 minus y0 square is equal to, you transfer this term to the right hand side. So it gives 4d square minus 4d square, that will be equal to 0, implies norm of x0 minus y0 is equal to 0 or x0 is equal to y0, and so the existed x0 is a unique element of M. Okay, means x0 is a unique element of M with the smallest norm. Okay. Similarly, on the same lines, we can prove the other theorem. If M is a closed linear subspace of a Hilbert space H, and if X is an element of H but not in M, and if D is the distance from X to M, then there exists unique y0 in M such that norm of X minus y0 is equal to D. Okay. If M is a closed linear subspace of a Hilbert space H, and if X is a vector in H which is not in M, and if D is the distance from X to M, okay, then there exists unique y0 belongs to M such that norm of x0 minus y0 is equal to D. Okay. So now, so for example, you consider, suppose this is the set, say this is the set like H. This is the set, say H, and suppose this is say M, which is a subset of H. Suppose X is a vector which is in H but not in M. Then what is the distance between the point and a set is the minimum of you know that minimum of the distance between X and M, every vector of M where M belongs to M. This you know that. Infimum of norm of X minus M where M belongs to M is the distance from X to M. Okay. So what is the distance from, we will find all the, suppose this is the point, we will find all the distances at each point, we will find the distance first. So okay, distances here. So among these, the smallest distance will be called the distance from X to M. So here this may be the point which is the smallest distance from M to X. That is, the theorem says there exists unique point such that there exists unique point of M such that the distance between M and X is, this is the distance. Okay. So this is the distance. Say we need to prove this in this theorem. Okay. Now by definition of distance between the point and a set, distance between X comma F is X comma M is D, that being find out by infimum of norm of X minus M or norm of X minus Z where Z belongs to M. Now by definition of an infimum, again there exists a sequence yn of vectors in M such that norm of X minus yn converges to D. X minus yn converges to D. Now consider the two vectors are any two elements of this sequence. Those are yn comma ym. Now since M is a subspace, linear subspace of H, therefore if yn comma ym belongs to M, then half times yn plus ym belongs to M. That is yn plus ym by 2 belongs to M, because by definition of a subspace, if x comma y belongs to M, alpha x plus beta y belongs to M, that alpha and beta I have taken to be 1 over 2. Okay. Therefore by definition of D, what will happen? Norm of x minus this vector definitely greater than or equal to D. Okay. Or multiplying throughout by 2, we get norm of 2x minus yn plus ym is greater than or equal to 2D. You call this by number 1. Now you apply the parallelogram law for the vectors x minus yn and x minus ym. We get norm of x minus ym minus x minus ym whole square is equal to, directly I have written 2 times norm of x minus ym square plus 2 times norm of x minus yn square minus norm of x minus ym plus x minus yn square. Okay. So this is equal to, this implies, so this becomes what? Yn minus ym square is equal to 2 times, you write as it is. Here the third term is 2x minus yn plus ym whole square. So this is less than or equal to 2 times, this is less than or equal to d square, this is d square, therefore 2d square plus 2d square, this the value of this is minus 4d square. According to 1, the value of this is minus 4d square. So the total is 0, the sum is 0. Therefore norm of yn minus ym tends to 0 as m and n tending to infinity. Therefore you can declare yn as a Cauchy sequence in M. Okay, yn as a Cauchy sequence in M. So but M is a closed linear subspace of H, therefore M is also complete. So since M is complete, there exists a point y0 in M such that yn converges to y0. Now norm of x minus y0 is equal to norm of x minus y0 can be written as limit of the sequence yn. So this is equal to limit of norm of x minus yn, but this is nothing but D. Thus y0 is a vector in M with the such that norm of x minus y0 is equal to D. Thus we have proved the existence of such point y0. Okay. Now we have to show the uniqueness of y0 here. again as in the previous theorem, you take any 2 points, say x0 comma y0 in M, such that norm of x minus y0 is d, as well as norm of x minus x0. X minus, say this is x minus x0 is d, and norm of x minus y0 is also d. Now as M is a subspace, again x0 plus y0 by 2 belongs to M. Okay, then by definition of d, what will happen? X minus x0 plus y0 by 2, this term is norm of this term is greater than or equal to d, or 2x minus x0 plus y0 is greater than or equal to 2d. Okay, so using parallelogram law again for the vectors x minus y0 and x plus y0, x minus y0, x minus x0, we get norm of, so we get norm of x minus x0 minus x minus y0 square is equal to 2 times norm of x minus x0 square plus 2 times norm of x minus y0 square minus norm of x minus x0 plus x minus y0 square. So this implies on the left what will get? Y0 minus x0 square is equal to 2 times norm of x minus x0 square plus 2 times norm of x minus y0 square minus, this becomes 2x minus x0 plus y0 whole square. But as m and n tending to infinity, this is less than or equal to 2d square plus 2d square minus 4d square, it gives 0. Therefore this implies norm of y0 minus x0 is 0, or x0 is equal to y0, means y0 is a unique point of M such that norm of x minus y0 is equal to d. Okay. Now let us take up the other theorem. This theorem says if M is a non-empty subset of a Hilbert space H, then M perb is a closed linear subspace of H, or M perb or M perpendicular. What is M perpendicular? M perpendicular is called the what is this space called? Orthogonal complement of M. You have studied inner product space, there you know what is the ortho. If M is a non-empty subset of Hilbert space M, then the orthogonal complement of M is denoted by M perb. By definition, M perb is what? It contains those vectors of H which are orthogonal to every element of M. It contains those vectors of H which are orthogonal to every vector of M. Okay. So we need to show this M perb is a closed linear subspace of H. But already you know that it is a linear subspace of H. We will show it is also closed linear subspace. Anyway, first let us take up showing this is a linear subspace as well as closed. Okay. By definition, M perb is set for x belongs to H such that inner product of x comma y is 0 for every y belongs to M. Now inner product of 0 comma y is 0 for every y belongs to M, right? By definition of an inner product. This means what? 0 belongs to M perb, and so M perb cannot be equal to MT, and so M perb cannot be equal to MT. So let x1 comma x2 belongs to M perb be arbitrary elements and alpha comma beta be scalars. Then for every y belongs to M, we have inner product of alpha x1 plus beta x2 comma y is equal to alpha times x1 comma y plus beta times x2 comma y. But x1 belongs to M perb means inner product of x1 comma y is 0. Inner product of x2 comma y is also 0 because x2 belongs to M perb. Therefore this becomes, total sum becomes 0. Therefore alpha x1 plus beta x2 comma y is 0 for y belongs to M implies where alpha x1 plus beta x2 lies. It lies in M perb. Thus for the elements x1 x2 belongs to M perb, and for scalars alpha beta the linear combination belongs to M perb implies M perb is a subspace of H. We will show this M perb is a closed linear subspace. Closed linear subspace means we will show that all the limit points of M perb are in M perb itself. So for this, let x be any limit point of M perb. Then by definition of a limit point, there exists a sequence xn in M perp such that xn converges to x. Now let y belongs to M. Then inner product of xn comma y is equal to definitely 0 because xn belongs to M perp. This implies limit of xn comma y is equal to 0. This implies inner product of limit of xn comma y is 0. This implies limit of xn is x. Therefore, inner product of xy is 0. Inner product of xy is 0 where y belongs to M implies x belongs to M perp. So, we have considered x to be a arbitrary limit point of M perp, and that limit point we have shown that it lies in M perp, means all the limit points of M perp are in M perp only. Therefore, M perp is closed. Therefore, M perp is a closed linear subspace of a Hilbert space H. Okay. Now, let us look at this theorem. Again, it says if M is a proper closed linear subspace of a Hilbert space H, then there exists a non-zero vector Z0 in H such that Z0 is orthogonal to the whole space M. Z0 is orthogonal to M. Okay. If M is a proper closed linear subspace of a Hilbert space H, then there exists a non-zero vector Z0 in H such that Z0 is orthogonal to M. Now, M is a proper subspace of H implies what? There are some vectors in H which are not in M. Okay. So, I have chosen the vector x in H which is not in M. Then x not in M means we can find the distance from the set x from the point x to the set M, that is d is equal to distance between x comma M, that is given by infimum of norm of x minus y where y belongs to M. Now, x not lies in M means x cannot coincides with y at any case. This implies what? X minus y is not equal to 0. X minus y cannot be 0 means this is always norm of x minus is always positive. Infimum of positive numbers is also positive, means d is positive. Okay. Now, just we have proved the theorem. If M is a closed linear subspace of a Hilbert space H, and if x is a vector in H which is not in M, and if d is the distance from x to M, then there exists a unique y0 belongs to M such that norm of x minus y0 is equal to d. This result just now we have proved. Therefore, by the above result, here since M is closed, there exists some y0 belongs to M such that norm of x minus y0 is d. So, you said z0 be the vector which is x minus y0. Certainly, z0 belongs to H because x and y0 are elements of H, and norm of z0 is which is norm of x minus y0 which is d, which is positive, means z0 is a vector with norm of z0 is greater than 0 means what? Z0 is a non-zero vector belongs to H. Okay. Existence of such z0 is assured now. So, we show this z0 is orthogonal to M. So, I will choose y is an arbitrary point of M. I will show that z0 is orthogonal to y. So, it then implies that z0 is orthogonal to M. Okay. Let y belongs to M be arbitrary and alpha be a scalar. Then y is also a point of M, y0 is also a point of M means y0 plus alpha into y be a point of M. Okay. y0 plus alpha into y, y is a point of M implies what will happen? The distance between norm of x minus y0 plus alpha y is certainly greater than or equal to d, or d square is less than or equal to norm of x minus y0 plus alpha y whole square. This implies d square is less than or equal to x minus y0 is z0, z0 minus alpha y whole square. So, this implies what? Norm of z0 minus alpha y square can be written as inner product of z0 minus alpha y comma z0 minus alpha y, which is greater than or equal to d square. Okay. So, this implies you expand the inner product. Okay. z0 comma z0 minus alpha y minus alpha times y comma z0 minus alpha y is greater than or equal to d square. This implies z0 comma z0 minus alpha is on the right. So, it comes out with its conjugate minus alpha bar into z0 comma y minus alpha into y comma z0 plus alpha into minus plus alpha into alpha bar into inner product of y comma y is greater than or equal to d square. This implies norm of z naught square. This is the norm of z naught square minus alpha bar into z naught comma y minus alpha into y comma z naught can be written as z naught comma y bar plus alpha into alpha bar into norm of y square is greater than or equal to d square. This implies norm of z naught square is d, so this d square cancels with d square on the right hand side. So this implies minus alpha bar into z naught comma y minus alpha into z naught comma y bar plus alpha into alpha bar into norm of y square is greater than or equal to 0. You call this by number 1. Now the relation 1, this relation 1 is true for all scalars because we are not made restriction on alpha. Okay, so let us take alpha to be beta times z naught comma y. This is a scalar where beta is arbitrary real number. Then alpha bar becomes what? Beta bar means beta because beta is real into inner product of z naught comma y conjugate or bar. Now putting the values of alpha and alpha bar in 1, we get say minus, this is alpha bar means minus beta times z naught comma y minus beta times z naught comma y bar into z naught comma y, okay, minus beta into z naught comma y into z naught comma y bar plus beta square into z naught comma y into z naught comma y bar into norm of y square is greater than or equal to 0. So this becomes what? Minus 2 times beta into z bar is mod z square. So minus 2 beta into mod of z naught comma inner product of z naught comma y square plus beta square into, again this is mod of z naught comma y whole square into norm of y square. This is greater than or equal to 0. Now you can take beta times mod of z naught comma y whole square as common. If we take this as a common factor, the remaining term is here beta remains, beta into norm of y square minus here only 2 remains. So this term into is definitely greater than or equal to 0. You call this by number 2. Okay. Now the relation 2 is true for all real beta. Suppose that inner product of z naught comma y is not 0. Suppose that inner product of z naught comma y is not 0. Then taking beta positive and so small that beta times norm of y square is less than 2. We can choose like such beta because beta times we choose beta so small that beta into norm of y square is less than 2. Then we can see from 2 that according to 2 that what will happen? Beta into inner product of z naught comma y square into beta norm of y square minus 2 is certainly we can choose beta so small that this expression is negative or less than 0. But this contradicts 2. This contradicts 2. Therefore, we cannot have the inner product z naught comma y should not be 0. So it should be 0 only. So this expression, in this expression, so z naught inner product of z naught comma y cannot be 0 because this expression, this is true for true. Okay. So we can choose beta so small that we can make the total expression less than 0, which is not possible. Therefore, inner product of z naught comma y must be 0. Inner product of z naught comma y is 0 means what? Z naught is orthogonal to y. Now y is an element of M. Therefore, z naught is orthogonal to y. Since z naught is arbitrary, so z naught is orthogonal to M. Since y belongs to M is arbitrary, z naught is orthogonal to M. Okay, so we have find such z naught, okay, in H such that z naught is orthogonal to every element of M. This is the theorem. Now we take up the last theorem of this class. Say before that, let us this definition. If M is a non-empty subset of Hilbert space H, then the orthogonal complement is given by set of all x belongs to H such that the inner product of x comma y is 0 for every y belongs to M. This is M perp. And what is orthogonal complement of orthogonal complement is denoted by M double perp. This is equal to again set of all x belongs to H such that inner product of x comma y is 0 for every y belongs to where? M perp. Okay, for every y belongs to M perp. Now here we show that M is closed if and only if M coincides with M double perp or M perp whole perp. So M is closed if and only if M is equal to M double perp. So for this, first let M be closed. Okay, let x belongs to M. Then by definition, what will happen? If x belongs to M, then inner product of x comma y is 0 for every y belongs to M perp. Now x comma y is 0 for every y belongs to M perp means by definition of M double perp, x belongs to M double perp. Therefore, M is a subset of M double perp. Yeah, M is a subset of M double perp. Suppose M contained in M double perp properly, means M double perp may not be a subset of M perp. Then what will happen? Suppose M contained in M perp properly. Then M becomes a closed, because M is closed, we have assumed M is a closed proper subspace of a Hilbert space M double perp. Then by the previous theorem, what will happen? There exists some non-zero vector Z0 in, then there exists a non-zero vector Z0 in M double perp such that Z0 is orthogonal to M. Now Z0 is orthogonal to M implies what? Z0 belongs to M perp. But already we have assumed that Z0 is in M perp as well as in M double perp. Means M perp intersection M double perp is 0. This implies Z0 is equal to 0, which is a contradiction to the fact that Z0 is non-zero. Therefore, it is a contradiction. Which is a contradiction means M perp, okay, M cannot contain in M perp properly, means M is equal to M double perp. Means M double perp is also contained in M. Okay. Conversely, let M is equal to M double perp. Now again, as M is a non-empty subset of a Hilbert space H, we have proved if M is a non-empty subset of Hilbert space H, then M perp is a closed linear subspace of H. We have proved. Okay. Now M perp is a linear subspace of H, and using the same result, we can see that M perp whole perp that we denote it by M double perp is again a closed linear subspace of H. Okay, understand now? If M is a non-empty subset, then M perp is a closed linear subspace. Again, you apply the same result for M perp, it can see that M double perp is also a closed linear subspace of H. But M double perp is equal to what? M. Therefore, M is closed. Okay. So, these are the few results for this class. Thank you.